I don't think so. Yeah. Are we good? Oh, perfect. All right. Cool. Hey, hello, everybody. Thank you for sticking around this late into the evening. I am Alain, and this is my colleague, Kelvin. We're both working in infrastructure in Uber in different teams. And today we'll be talking about using locality-sensitive hashing in Spark, and in particular to solve a problem that is very important to us, which is detecting multiple trips out of a large bag of trips in a city and over a large period of time, detecting multiple trips that are similar to each other, and the keyword being similar, not equal. Okay, so trips are routes, same thing to us. So this kind of gives it a more geometric definition to them. Okay, so what is the problem in particular? So if you guys are not familiar with Uber, we handle our basic entity, a basic business entity is a trip, right? A rider gets in a car and goes around, takes a ride for in a city. That generates GPS traces that we capture. Now, for multiple reasons, we want to determine what are the traces that are similar to each other. That gives us the idea of where people are going together. That gives us the idea of opportunities where we can do pooling and things like that. Now, what are these? How many trips are we talking about? We're talking about many, many, many trips over the period of weeks that we want to look at. The data itself is noisy. We're talking about capturing data from mobile devices that are moving at different speeds in different cities around the world that have very different signal quality. Again, we're not looking for exact matches, and one thing that is key is also is the directionality is important. So when we're looking for two trips that overlap, we're not just looking for trips that are going in opposite directions and on the same street and end up completely overlapping each other, but we actually want two trips that more or less start in the same area and more or less end in the same area. Okay, so what does the input data look like? So the input data is an ordered list of tuples. Each tuple primarily has a latitude and a longitude. It also has some extra information such as the epoch, the speed, etc. These tuples, the latitude and longitudes are reals, right? So they are two numbers, two latitudes and longitudes that would effectively overlap for all practical purposes. They're probably going to come in with different values, right? So you're going to see, you're going to see like a 25.7613 and a 25.7614, effectively the same thing, but not if you're just looking to do direct numerical comparison. So as I said, the input data has noise. Another interesting tidbit here is that you can get both sparse and dense traces. So if you have a vehicle going through a tunnel, you're going to get into the case where a cell phone with very good reception can give you data points all along the tunnel. So you get a nicely dense trace. But if a cell phone with a really bad reception or connected to a really bad provider in general, it's just going to give you a data point from the beginning of the tunnel and a data point for the end of the tunnel. Effectively, though, when you connect from A to B, if you know that order by the timestamp, they're sequential, it's still the same trace. So you still want to detect those two. Okay, so another interesting, so you're also searching over, imagine you're searching over, let's say we're doing a search in the area, in the Bay Area, right? So we have traces that come in over several weeks over the entire Bay Area, and these traces can be of multiple lengths. We could be traces that are as little as 3 points, which maybe was a quick request and a cancel. Traces that are stationary, mostly in a place, because maybe the driver arrived and started collecting GPS data, and the rider never showed up, so the traces are all on top of each other. You could also have traces that go all the way from San Francisco to Palo Alto, or down to the South Bay. Same thing in large metropolitan areas in China. Excuse me 1 second. Okay, so before we go into how we solve the problem, which ended up just being a combination of multiple basic concepts, let's go into those concepts. So the first one is Google S2 cells. So what is this? This is basically a way to take a point, a latitude and longitude point, and convert it into a long. But what is that long? It's effectively you're taking the sphere of the world, of the Earth, and you're hashing it into similarly sized geographic areas. And you can adjust the size of the areas, what they call levels. So you can adjust the size of these areas to the level of granularity that you're looking for. So if I were looking to match trips at the street level, I would go with something like a level 17 that splits a block into several blocks, into several areas. If I'm looking to more or less capture trips that more or less go along the same highway between like San Francisco and San Jose, I would use a higher level. Okay. So another relevant concept here is the Jaccard index, also known as the set similarity coefficient. What is this? This gives us an idea if we have two sets, two discrete sets. It gives us a single number that indicates how similar, or rather how overlapping these two sets are. Now, the key concept here is that it's not just about containment. It doesn't just tell you if you have, let's say one set A, B, C, and another set A. The Jaccard index of A, B, C, and A is actually going to be fairly low because there's a significant component of the first set that is extra. So it's effectively the cardinality of the intersection of the two sets divided by the cardinality of the union. So you can see you have set A and C as the two extremes. A Jaccard distance to A is going to be 1, and A Jaccard distance to C, where they only have one overlapping element, would be 0.2. Okay, so how do we put this all together? Okay, so the first step of the heuristic is to densify all the points. This will become apparent why it's useful in the next step. Excuse me here, I'm still recovering from a sore throat. Okay, so as I said, 2 points, 2 devices that capture the trace going through a tunnel from A to B. The 2 traces will look like this. You will have A to B, and you will have maybe just 2 points, and the other one has many points in between. So the blue points that you see on the right are the points that we would have inserted. So we determined, hey, you know what? We want points every 10 meters, and so we just insert points at a minimum set of intervals. So where does this become useful? Okay, let's see into the next step. So the next step of the heuristic is that we take those S2 cells, and we take all of these points, and we map them into an S2 cell ID. Now you can see that, if you can see that we have 2 traces that begin at the bottom being very similar and very overlapping, but then they diverge towards the end. Now that section just before they completely separate, that is still effectively for us, effectively overlapping, right? And you can tune the size of the cell level that you want to use to determine the level of overlap that you capture. The discretization also helps you determine 2 trips that started at pretty much the same location, but maybe one stayed put for the first 5 minutes and continued, and the other one just took off right away. They're still effectively the same trip, and they took the same route. So the discretization, by mapping them, then you can do a reduce on the same ID, and you deduplicate them. Okay, so let's see. So the final thing here is, okay, so now we've converted a trace of continuous reals into IDs, into longs, right? This is effectively a bag. Now, if we wanted to use this set overlap problem with just these IDs, two traces going from A to B and the other one going from B to A will look exactly, it's the same set of longs, right? It's the same set of IDs. So what we do is we actually use this concept of shingling, which is pretty much taking any 2 contiguous points and grouping them into a tuple. For the very simple use case, we just take every 2. So 1 to 2, 2 to 3, 3 to 4, etc. If you look at this as unique IDs, effectively, what do you have? You have now the same point that was towards B, it's 7 to 8, but for the trip going in the opposite direction is 8 to 7. When you hash these, they're going to hash to different values. So now you've effectively captured directionality. Okay, and so the interesting bit here is like, well, what do you have now? Now you've reduced the problem of, wow, I have all these GPS points that go from A to B, and they're all over the place, and I have no idea how to correlate them, into just a set overlap problem. We just have all this bag of longs, and this bag of longs on the other side, and we just want to know, any two bags of longs that end up overlapping with each other. In principle, or conceptually, this is very simple. Now, how do you do this at scale, right? How do you do this in a distributed manner? That's where the interesting bit comes in. So, your first approach is n squared. Let's just compare every single one of them, and we're not just looking for individual pairs, right? We're actually looking for clusters of them, because oftentimes you end up with like, hey, 3 trips that look very much equal to each other, and we want to know them in that group. We don't want to know that the 2 and 2, the different combinations of them. We want to know them in a cluster. So in the first attempt, just to validate the heuristics, I went ahead and tried the n squared approach, and it basically didn't even finish for the data set that we needed to complete over. And this is where locality-sensitive hashing comes in. And because we've also reduced the problem into the individual data points or longs effectively, this is something that Spark ends up being very good at. And to go into the details of that, my colleague, Kelvin.
Thanks, Alain. So next, I am going to talk about locality-sensitive hashing, LSH in short. So LSH is not a new idea. So basically, the research community introduced the idea almost like 20 years ago. We don't invent that. We just use it to solve our problem. But I'm still going to give a quick introduction, like what is it. So basically, LSH tries to solve some problem, and one of them is called near label search problem. So the setting is given a set of points, P, and a single query point Q, and also a distance function D. So the distance function D can compute the distance between 2 points, and the return is a single numerical value to tell how similar the 2 points are, right? So the problem asks for to return all the points in P, which is similar to Q. And the second problem LSH can solve is clustering. Again, like given a set of point P and a distance function D, the problem asks for to return all the pairs in P, and they are similar to each other. So to solve the problem, like let's say in some low-dimensional space, for example, like one-dimensional space, right? Let's say you have a set of integers. The solution can be like pretty easy, right? You index the integer by binary tree, and then you just traverse the tree, and during the traversal, you return all the integers similar to your query, right? And then in two-dimensional space, actually, like let's say you have a collection of GPS points, right? You can still solve the problem like by some advanced data structure like quad tree, R tree. They work very well like for dimension, like let's say less than 10. So the real challenge is like you have a very high dimensional space. For example, in align approach, right? A single trip can have thousands of shingle, and each shingle is one dimension, right? So that means like a trip can be represented in a very high thousands dimensional space, and it becomes very hard for any algorithm or data structure to solve the problem like exactly. And this is how LSH can help us to solve the problem. And it is an approximate algorithm. It means that the answer given back by the LSH algorithm is an approximate solution. So the algorithm asks one question, and the question is, let's say trip T1 and T2, they are similar. The question is, like, is there a hash function which can hash like both T1 and T2? And if they are similar, with high probability, they will be hashed into the same bucket. The question is, like, is there such a magical hash function? And also, similarly, if T1 and T2, they are not similar, the same hash function, will they hash the two trips into two different buckets with high probability? So this is the question LSH asks, right? And it turns out that for some distant function, we can find some good companion hash function for them to achieve those two desirable properties. And Jaccard distance that we are using in align algorithm is one of those good distance function. And the min hash function for Jaccard distance is that function which has those two good properties. So the definition of min hash function is the input is a set, and then we hash every element in the set to a hash value. And then the minimum value, the smallest value, or the smallest like hash value is the mean hash value of a set S. So let's take an example. Let's say we have a set of 3 elements. We apply the hash function to every element in S, right? And then we get back like 3 hash value. In this case, 1 is the smallest one, and it becomes the mean hash value of S. So Jaccard distance is just one example, right? So the research community, they found out like actually a lot of distance function like also can have such a good companion hash function. Other example is like Hamming distance, cosine distance. They can also find a good hash function for them, and they are also useful in other like applications. But in our case, for our trip similarity problem, we use a Jaccard distance. Cool. So we know that, hey, like we have this hash function, right? The next question LSH asks is like, how can I control the probability, right? We want to have good probability to catch similar trips, right? And again, it turns out the solution is very intuitive, right? Let's use multiple hash function. Let's hash it multiple times. Let's say in this example, H1 and H2, they are both mean hash function, but they use like different parameter A and B, right? So we construct multiple mean hash function, and then for every trips in our data, we apply every hash function to them, and then hash them to different buckets. So we went over like the theory, the algorithm part of the LSH. Next, I'm going to talk about how to, what is our approach to implement it on Spark. So the idea is also pretty simple. So let's say I have a bunch of trips. So we use it to construct a RDD of trips. And then we iterate over like the RDD. For every trip in the RDD, we use all the hash function to hash them into different key range. So the trick here is every hash function will have their own long overlapping key range. In this example, T1, T2, they are hashed by H1, and they are in the same H1 range. Similar for the H2 hash function. And then at the end, the hash value become the shuffle key. We have a bunch of keys, which is the hash value. And then we call the group by key API on top of this RDD. So, and then after the shuffling, right, we have a bunch of trips. They are hashed into different like buckets. And then we have a post-processing step. Because like in theory, right, if T1 and T2, if they are in the same bucket, then they are likely that they are similar. So what we do in this step is like for every bucket, in parallel, for every pair of trip object in the same bucket, we actually compute the Jaccard distance between them, right? So if they are actually similar, if the distance value is small enough, that means like they are similar enough, then we will report them. Otherwise, we will just ignore them, right? There will be, like in theory, there will be some like false alarm that like different trips, they still hash in the same bucket. We will filter them out like in this step. So that was the approach number 1. Here I'm also I'm also going to discuss the approach number 2, which is very similar to the approach number 1. So the difference is in approach number 1, like it is possible that the same pair of trip object they are hash and match in more than one bucket because different hash function, they hash them into the same bucket. Like in this example, like T1 and T2, both H1 and H2 hash them into the same bucket, right? That means like the Jaccard distance computation will be done 2 times, each in the different bucket. So for some distance computation, they are actually very expensive. And this become a trade-off between the network shuffle and the distance computation. So in approach number 2, we suggest that, hey, we can do one more shuffling to do the deduplication, right? So we pay the time on one more shuffling. However, we will save the time on repeating Jaccard distance computation. And there's no clear answer that like which approach is better. It depends on the use case, right? It depends on like how expensive is the distance computation, and also how fast is the network. We actually need to run the experiment and do some actual performance measurement to decide like which approach is better. And it varies like case by case. And we also try one more approach. And this approach is also very similar to the last two approach. And the optimization strategy here is for some object, and in our case, which is the trip, right? The trip object can be very large. It can have like many shingles, right? And then shuffling a very large object across the network can become like very expensive and slow, right? So this approach, what it suggests is like, okay, in the first two shuffling, let's not actually shuffle the object. Let's just shuffle the trip ID, right? And then at the end of the second shuffle, you have finished the deduplication, and then you actually join back the trip ID pair to the real object with more shuffling, right? And the trick is like, okay, then now you become to compare like whether like more shuffling in this case, is it like more expensive compared to actually shuffling the large object. And again, like there's no clear answer like which approach is better. We actually need to run experiment and measure the real number to see which approach is better in which use cases. This is another optimization strategy, which is, so in LSH, right, we need to come up with a lot of hash function, right? So that means like we need to generate a lot of tuple of the hash parameter A, B, and M. And it means that like in the CPU level, you need to like keep like changing this tuple to use them to hash the trip object. So, so we did some research online and found out actually the research community has like other approach to generate a bunch of hash function. So let's say, for example, we can actually just use two hash function, and then use those two hash function to generate 1,000 of different hash function. And the idea is like, let's say I want to generate 1,000 hash function, then we just use a different multiply, and we use the same two hash function to generate all the other like 1,000 hash function. And it is better in some cases because like the CPU can cache only two tuples of A, B, and M in the CPU register and or the L1, L2 cache. So other features we also implement in our library, but we haven't like go into the detail in this talk, is the amplification. So which is also a LSH strategy to have to improve the probability of true collision and avoid the false alarm. We also implement feature for to support a linear label search, but we don't cover here because of the time. And also, we just want to mention that, like, in our case, we use LSH to detect similar trips. However, like, LSH can also be applied to other problems, like, for example, detecting similar document, similar images, time series. Also, for people can also use it for product recommendation. Some future work that we are also going to work on is we are going to migrate our API to the Spark ML API in version 2.0. In the future, we hope that we can contribute the code back to the open source Spark source code. We also plan to implement features for Spark streaming. Cool, that's it of our talk, and any question, welcome.
All right, fantastic. Do we have any questions? Right here.
So on the LSH approach, after you apply your mean hash, did you do a secondary hashing on those mean hash? Like, picking the band and the row
Yes.
to kind of getting better performance and
Right. So the question is like, do we like do the second hash on top of the first hash? And the answer is yes. Our libraries support banding, amplification for different distance function. It's just that like for the time of the talk, we didn't go over it.
Any other questions? Oh, sorry. Over here.
Hi. I was just wondering, could you define exactly what you mean by fraud? Like, I know that people are going on multiple trips and they're following similar paths, and maybe they're like starting and stopping at the same location. But could you just kind of like explicitly say what is fraudulent about the trip?
Do you think you can answer this question?
I think the short answer is I can't go into the details of of that. In general, the problem is of interest to fraud because we would like to find trips that are taking traces over time, that are taking trips over time, through very similar routes. I can't go into any more details, unfortunately.
Anybody else? All right, I don't see any more questions, so let's give our speaker one last round of applause.